We're here again at the tutorial stage of the lecture, and I'd like to start this tutorial by first pointing out a small change in the layout of the tutorial. Notice that before we had a single notebook that I called assignment.ipynb, but that for this tutorial, I've broken the notebooks out into three parts that will talk about sort of the three components of the tutorial, and each of these has at the very end the learning assignment or learning exercise, as well as a self-assessment that you will fill in. I'm going to assume at this stage that you're familiar with how you interact with these notebooks, given that you've done this for two other assignments. So I'm not going to spend much time speaking about the layout of the notebook, but just dive into the tutorial directly. Okay, so let's start with part 0, which is going to be a discussion of existing corpora. So first, recall that in the previous two tutorials, we began with reviews on how to use the requests library in Python. That was for collecting HTML pages. And then we also even did some HTML processing by introducing tools like Beautiful Soup. Now, we did those exercises together because I want to help build your familiarity and confidence with collecting your very own NLP dataset. It's an essential skill for many practical research problems, or if you're going to go to industry, those skills are going to be important too, especially if there's not a well-curated, publicly available dataset yet. Now, note that creating useful or interesting new datasets is actually an effective way to build your reputation in the scientific community and beyond. Big advances, for example, to Google's release in their language translation system were all based on sort of curating and collecting better datasets, or not completely, but to a large extent were based on that. So collection of interesting new datasets is a good skill to have. Okay, but now that you're familiar with how to collect your own data, I think we can focus for the rest of the course less on the onerous task of data collection. After all, if you're interested in making a career in the development of new NLP algorithms, you'll probably only be able to prove that your algorithms are better by comparing their performance against others who've tried to solve that same problem before you did. And to do those tests, you'll want to be able to access established datasets with established structures, including the way that the investigators before you split the data into the training, the validation, and the test folds, so that you can train your model on the train, validate on the validation, and test on the test. Now, in this spirit, let's spend some time reviewing how to access and leverage data resources that already exist and are freely available online. One resource, and that's actually pretty recent, to help you obtain access to NLP datasets is the Hugging Face Datasets library. And it's just a very lightweight and extensible library that allows you to quickly download the popular NLP datasets onto your machine. So let's start by importing the library and taking a look at some of the datasets that are available through the repository. You can see here, I've imported some of the tools from the Hugging Face dataset library. And I can get a list of the data sets, and I'm going to just print them down here. And you can see that there's a whole bunch of them. There's actually 164 data sets available on the hub at the moment. And you can actually just by glancing at some of the items in this list, guess what some of the content is. For example, you'll notice that Wikipedia has an appearance on here. Yelp polarity shows up here, so clearly these have something to do with Wikipedia and Yelp data. There's a bunch of other ones sort of scattered throughout this. Other data sets have far more mysterious names, which you could obviously Google around to sort of figure out. But fortunately, Hugging Face has put together a convenient data set viewer page. So I'm going to open it here so that you can see it. And this data set viewer page will allow you to select a data set that you might be interested in. For example, I could do this one clue, and it will tell me the homepage that sort of is responsible for contributing this and a description of what this clue data set includes. In this case, it's a Chinese language understanding evaluation benchmark. And you can sort of read through the documentation here to get a better understanding of the data set. Okay, so let's start the tutorial by downloading the Rotten Tomatoes dataset from the Hugging Face library. Okay, so what I'm going to do is very simply first call load dataset, Rotten Tomatoes, and this Rotten Tomatoes here, I got it from the list that I showed you up here earlier. Okay, and then I'm just going to start by printing some of the characteristics of the data. That's all this code block does. Okay, and if I print those characteristics, I can see it consists of 8,500 or so training data points, 1,000 or so validation points, and 1,000 or so test points. And if I want to see what the data is roughly formatted like, I can just print an example sentence from the training data set. The Rock is destined to be the 21st century's new Conan, and he's going to make a splash even greater than Arnold Schwarzenegger, Jean Van Damme, or Steven Seagal. Now, these example sentences have labels, okay? And the labels in this case are binary. They're 1 and 0. You can sort of see what those labels mean if you navigate again to the Hugging Face library page. I'll just tell you that the labels actually here refer to whether the movie review from Rotten Tomatoes was positive, which is encoded by a 1, or negative, which is encoded by a 0. Okay, and you also notice that the data is obviously partitioned into its train, validation, and testing splits. That's really wonderful if, for example, you had some brand new super fancy algorithm and you wanted to prove that you could classify movie reviews better than anybody else in the world on this Rotten Tomatoes data set. Okay, well, the Hugging Face library doesn't just contain access to these nice data sets, but it also contains access to certain metrics that are new and upcoming in the NLP community. So remember that in the last exercise, we actually spent some time performing and creating metrics for the evaluation of language models. We used perplexity, for example, in one part of the last homework, and then you wrote out your own function for the AUROC, the F1, the accuracy, and so on from the confusion matrix. Now, I had asked you to spend some time writing those performance metrics yourself from scratch in the hopes that by writing it out, it was going to remove the mystery from those metrics. Okay, they're just computations. They're sensible computations based on certain properties that you want to measure about your model, right? Okay, and the critical thing that for you to take away is that you're choosing how to measure the success or failure of your model, and that the appropriate metric usually depends on the specific task and the constraints that come along with that task. Okay, there's nothing that actually stops you from creating your own performance metric if it doesn't fit your task well. And in fact, the creation of performance metrics is a domain of research in its own right, which is why the Hugging Face library provides access to new and upcoming metrics. So that is to say that many of your peers in the computer science community are diligently working to propose better ways to compare models as a function of the tasks, the objectives, the constraints. So BLUE, for example, is a popular metric for machine translation work that's known to correlate well with human judgment. So basically, you give it a sentence in one language, you give it a sentence in another. This BLUE metric helps you figure out how well the translation worked. And you can then go about comparing your translation model against my translation model using BLUE. I've included a link here, by the way, in case you'd like to read the article on the BLUE score. You don't have to, but I'm just putting it here for your reference. Okay, well, the critical thing here is that you probably don't want to have to re-implement BLUE like you did for AURC, F1, and accuracy unless you absolutely have to. It's great if you do, but you may not want to have to re-implement them. So the nice thing is that Hugging Face, their library, has provided some implementations of BLUE and several other scores. BERT score, for example, is on there as well, that you can just very easily load in. So let's start by loading in some of those metrics. Okay, here's the line of code that we run to do that, and you can see that there are 13 metrics that were available when I ran this. Okay, and similarly, you can go ahead and print a description of these metrics from directly within the library if it's mysterious what these metrics do. And you can see that a description of the metric gets generated below. Okay, so now let's move to the classification component of the tutorial. Remember that last time we were dealing with classification for philosophical texts. We were basically trying to figure out, hey, given that I have some text, can I figure out if this text was generated from Nietzsche, or can I figure out if this text was generated from Russell? And we built a whole bunch of classifiers around that topic last time. Well, for these purposes now, moving forward, so that you can get familiar with using Rotten Tomatoes dataset and other publicly available datasets, let's kind of bid those philosophers goodbye and instead focus on the movie reviews. Okay, so I'm going to start off by importing the Rotten Tomatoes dataset. I'm then going to, just for the purposes of training a simple model, I'm going to flatten and combine all the three, the training, the validation, and the test sets into a list called sentences. And I'm going to get the labels of those sentences. These are binaries, ones and zeros, that I'm going to put in a variable called y. And then, as you probably recall from the last tutorial, we can use bag of words to find a representation of the text using this count vectorizer function. And so I can just very simply convert my sentences here to a matrix X using the count vectorizer function. Okay. Now, the next thing that I'll want to do is split this into training and testing sets. Please note that I'm doing the split here just for illustrative purposes. In reality, we could just take the training data set from here and the test data set from here and sort of transform them separately. We could do that as well. Again, I'm just doing this here because I want to show you illustratively how to do that. Okay, the above code, I hope, is familiar to you from the last tutorial and from the last homework that you did. Basically, we're taking the movie reviews, we're creating a simple list and of the input sentences and the output labels, and we're putting these to bag of words so that we can use them for classification purposes. And remember that in the last assignment, we used the logistic regression model from sklearn. So let's go ahead and try that in this case as well. So you can see here, I've imported from sklearn the logistic regression. I've imported the confusion matrix and some other things. And the first thing I'm going to do is I'm going to initiate 4 logistic regression models, each with a different penalty function. So remember from the last assignment, I asked you to train a basic logistic regression model. That's this. I'm going to train another one that has an L2 penalty, another one that has an L1 penalty, and then another one that has a elastic net penalty. And recall that the elastic net penalty has a ratio between the L1 and the L2 loss, which I've specified to be 0.5 in this case. Okay, and then I'm going to fit all 4 of those models, as I show you down here. I'm just going to store them in a nice dictionary of models, okay, so that I can keep track of them for later when I want to print. And I'm going to obviously fit them by passing in the training data and using that to create the models. Okay, well, now that I've trained the models, I can go about assessing their performance on both the training set as well as the test set. So this code block here is just my way of showing you how, from scratch, in case you struggled with the previous assignment, you can go about generating each of the elements of the confusion matrix so that you can plot the AUROCs from scratch. Okay, that's all this code block does, but effectively all we're doing is computing the AUCs on the training and the test set in this big code block, in case you're interested in seeing it. Okay, and if I plot them here, what do I notice? I say, well, okay, so here's the regular logistic regression, the blue line. Okay, and then the logistic regression with the L2 penalties in orange, the L1 penalties in green, and the elastic net one is in red. And I've got it for the training data here in the left plot, and then I've got it on the testing data here in the right plot. Now, what you're going to notice is a couple of things, right? First, recall that the AUROC, when it has a 1, that's the best value you can get. And with that in mind, the model is performing excellently on the training set. In fact, all of them are performing excellently on the training set. And they're actually performing pretty well, I would say, on the test set, especially when you consider that this bag of words representation is just simple unigrams. And so it's insensitive to things like the word order and so on and so forth. Okay, but as we compare the differences in the model's performance across the training and the testing sets, what you're going to notice is that the logistic regression model, the blue line here, without the regularization, it did phenomenally well on the training, right? It has 0.99 AUC. But then if we come and we look at its performance here in the test set, it actually has the worst performance of all four. Well, the reason that there's this discrepancy between these two is because of a phenomenon known as overfitting. That's when you basically have a very significantly large number of parameters that your model can play with in order to optimize its performance against. And if you think about the bag of words representation, we have one parameter for each of the units in the vocabulary, and that's a really phenomenal number of parameters, right? The reason that when we compare the performance, for example, of, let's say, the orange line here, which is the L2 penalized one, we don't see as big of a drop in performance. We're going from 0.99 now to 0.85 in the case of the L2 penalized model, is because we're basically punishing the model by adding that penalty for gratuitously adding parameters it doesn't need. So it has to sort of be careful with how many parameter values it tunes to be non-zero, and this improves the generalization of the model to new data it's never seen before. Okay, so one of the things that is tricky though about choosing the hyperparameters, right? If we scroll up to this code block here, let's come up here again. You may recall that I had a hyperparameter here, right? L1 ratio that I just arbitrarily set to 0.5. Well, one fair question you could ask me is, how did you know to set that to 0.5? Why not 0.4 or 0.3 or 0 or 1? Or how did you exactly tune that? And the answer here is that I kind of guessed at this, right? I didn't know for sure what the right value of the L1 ratio is, so I just chose a value arbitrarily. And so obviously the performance of the model you might expect would change as a function of that L1 ratio parameter, as well as other parameters that exist in the elastic net. One of the things we didn't touch, but we left as the default, was another parameter called C that says how powerful is the regularization. Okay, well, one thing I could do is, if I wanted to understand intuitively what the relationship is between these hyperparameters, the L1 ratio and the C, and the performance of the models, I could just try many, many different values of them and then plot the performance. Okay, so this code block down here is just me doing that. Okay, and you're welcome to read through it if you'd like some specific intuition for that. So I'm generating, to be very clear, basically a heat map, which I'm showing down here, which says, as a function of those two parameters, the C parameter and the L1 ratio parameter that went into the elastic net, what was the performance of the logistic regression model on the test set? So notice here that the darker the value is, the worse the AUC is, the performance of the model on the test, and the lighter the value is, the better the performance of the model is on the test. So if I just kind of, glance over this, what I notice is, hey, the performance seems to be best when I'm in this bottom left corner. In fact, we're getting a huge difference in the AUC, I would argue, almost of 0.2 if we're in this bottom left corner versus the bottom right corner. I bring this to your attention because the hyperparameter settings in most models are not formally optimized by the methods. So you don't use, in logistic regression, it doesn't choose those hyperparameter values for you through any kind of formal optimization approach. These are things that you have to set. And I bring this to your attention because sometimes the difference between a model that performs very well and a model that does not perform very well is how you set these hyperparameters. And all this image here is meant to illustrate and demonstrate to you is that you should try exploring those if your models perform poorly. Okay. Well, as I mentioned earlier, one of the things that can contribute towards overfit in logistic regression, remember how that blue line, for the regular logistic regression with no penalty, it was fantastic on the training set. AUC was 0.99, but then it sucked on the test set. Okay, well, the reason for that was because there was just too many features. So specifically, the number of features, if we just kind of look at the size of the training set here, was 18,000. I mean, that's a huge number of features. Now, I'm sure all of you at this point in the class, given some of the memory challenges that you ran into when trying to represent the language models from the first two assignments, can appreciate that, yes, like the number of unigrams or bigrams or trigrams can grow really, really quickly when you're dealing with these sorts of data sets. But this is particularly problematic. Why? Because the number of columns we have in this data set, the 18,000, is actually even more than the number of rows. And so if you want to think about this from a formal statistical perspective, we don't have enough degrees of freedom to even train this model properly, right? So it's pretty surprising, actually, that it was able to do anything effectively on the test set, given that there's so many parameters it was able to optimize relative to the number of data points that we have. Now, the other thing here is that you and I both know intuitively at this stage that not all these unigrams in the data are created equal, right? I mean, some of them are stop words. They're words like a and the and at that are probably not going to contribute to our ability to predict whether a movie is going to get a positive or a negative review on Rotten Tomatoes. And so one of the things that we might do, a very simple thing that we might do, is to look at the frequency first of the unigrams in the text, which is what this code block does. I basically come here and I'm counting up the frequency and I'm kind of printing it out for each of the unigrams. And what I notice is that so about 42% of the unigrams occur just once, 14% occur twice, and so on. This is just the same old observation from Zipf's law, the thing that we mentioned in the very first lecture when we were speaking about the properties of language. Okay, so a simple thing that we might want to do is see how well the logistic regression performs if we just throw out these unigrams that are only occurring one time, because if they're only occurring one time, they're taking up a ton of space. They're probably not providing a huge amount of information for a classification purpose because they literally only ever show up once. Okay, so let's just toss them out and see how well our logistic regression model does. Okay, that's what this is doing. We're just chucking out the things and we're going to replot the performance as a function of the amount that we toss out. Okay, and what I've generated here is actually two plots that again speak about the training performance of the model. The blue line here again refers to the logistic regression with no penalty, just so that we're totally clear. So I've got the training performance of the model, and you can see that the training performance is no longer 0.99. Okay, at least it's not 0.99 as we reduce the bag of words features to be smaller and smaller. So, for example, if I use only the first 1,000 most highly ranked features in the bag of words, you can see I get an AUC of about 0.88. And if I correspondingly come here and look at the performance in the test set, I get an AUC of around 0.79. And obviously, as I increase the number of features that I include that are ordered here by rank, I'm going to improve the performance of my model to do well in the training set, but the performance in the testing set sort of levels off at some point, as you can see here. And eventually, in fact, should go down for many problems. So, but what does this sort of plot, in an essence, sort of tell us? This plot tells me, at least, that we can toss out everything except the first 1,600 or so words by rank. Those are words that have an occurrence of 12 or more, by the way. And then we can, in fact, improve the performance of that standard logistic regression from the 0.77 it was before, when we were using all 18,000 kind of points in the bag of words representation to just a relatively small representation of just 1600. Okay, well, so this is great, right? That, we were able to reduce the size of the bag of words representation with no cost to performance just by sort of figuring out which words to toss out. Now, remember that the whole point of the regularization was to identify those features that weren't worth assigning weight to automatically. So what we did here together by rank ordering and throwing stuff out, the hope is that the regularization through L1 and L2 penalties kind of does that process for you. Okay, but one of the things that's interesting about this bag of words representation that we have currently is that it does not account for the fact that certain terms might be, let's say, highly correlated in the sentence. So it might be that, for example, we're talking about movie reviews, so maybe Steven always shows up with Seagal. Okay, maybe those two unigrams always show up in the same sentence. And so if they always show up in the same sentence, then the information is redundant. We can actually represent those two columns in our data set as one, which captures the two together. Now, remember from the lecture that we said one of the ways you can go about accounting for those correlation structures in your data and finding another way of representing it that eliminates that is through principal component analysis, okay? And I've again included a link here to principal component analysis in case this is the same thing that we talked about in the lecture, just to help you sort of intuitively understand the way that PCA works. Okay, so let's take PCA and let's see if we can condense the size of the word vectors down further from the 1600 dimensional representation to something even smaller. Okay, so first I'm going to apply principal component analysis. That's all this does. Okay, and now what I'm going to do is I'm going to say I need to choose how many of the principal components to keep. We had 1600 of them that came in as the input to PCA, so we're going to get 1600 principal components. But remember, just like we saw in this example over here, depending on the way the data is shaped, not all those principal components matter. If my data, for example, looked like this, only the first principal component is really relevant for me to keep. So what I want to do is I want to figure out how I can throw away some of the principal components that have very low variance, okay? So the variance basically principal component 2, as you can see here, is extremely low. That's why I can throw it out. Okay, so similarly, I can come here and I can sort of take the cumulative sum of the variance from each of the principal components and I can plot them. So here what I'm doing is I'm saying, tell me the sum of the variance from principal component 1, 2, 3, 4, 5, 6, 7, all the way up to 200. And this is cumulatively summing up all the variance that's accounted for. And what you can see is that obviously as time goes on, this gets less and less steep, this curve. Why? Because the principal components are rank ordered for you. So obviously the less important or the ones with less variance are going to come later. And so this curve of the cumulative sum of the variance accounted for by those principal components is going to start to flatten out. Okay, well, one thing I might do that's common practice in the machine learning community is say, I'm just going to figure out at what point I get 90% of the variance captured by these principal components. And the rest of these, everything on this tail end, the other, in this case, 750, 850 or so, I'm just going to throw them out. I just don't even care about them. They're not contributing enough to the variance. Okay, so all of that is to say that I could re-represent that already sparse representation, the 1600 column bag of words representation that I reduced down from the 18,000. I can make it even smaller by using principal component analysis at very small costs to the total amount of variance that's captured in that data. So I can keep essentially the first 750 principal components and represent my data that way. Now, you may not believe me. You might think, oh, this guy, Gassimi, who knows, right? Seems like how could you capture the same amount of information in 750 columns as you do from 18,000? Well, let's just go ahead and test it, right? Let's put it into a logistic regression model and see how the AUROC changes. And what you can see from this little code block is that it actually doesn't change at all. I can use think about how crazy this is. I can use 750 dimensional representation of my sentences instead of an 18,000 dimensional representation at almost no cost to my model's performance or generalized performance on the testing set. Okay, so in this first learning exercise that you're going to be completing, I'm going to ask you to do a couple of problems that are going to hopefully enhance your familiarity with principal component analysis and simple ways of representing word vectors that are context-based. So the first thing that I'd like you to do is I'd like you to do a principal component analysis coefficient interpretation. We used PCA earlier in this tutorial. Your goal here will be to basically find a way to take the coefficients of a model that are trained using the principal components and reverse engineer out the coefficients in terms of the original variables for that model. The reason that that's possible is because, once again, remember here, because the principal components are always linear combinations of the basis vector, what that means is that I'm going to describe this red line here, the first principal component, in terms of x and y. It's some linear combination of x and y, and the green line is as well. I should therefore, with the red line, be able to reverse engineer out, if I had some value along this red line, I could project onto x and project onto y to get it. Okay, let me be very, very clear here. So let's look at this data point here. I'm going to actually move this so that it's very clear what I'm talking about. Let's look at this data point here that's right at the end of the red line. Okay, and I'm going to come over here. This is the principal component representation here on the right-hand side. So notice here that this point, which is, I don't know, let's say 1 along principal component 1, notice that this point actually, if I turn the axes back, it's this point here, which corresponds to 5 on x and 4.5 on y. So my point is that as soon as you have the information that allows you to rotate the axes here from this xy representation to the principal component representation, you can take any point in the principal component space and reverse engineer it into the xy space. And I'm basically asking you to write something to do that if you wanted to interpret the coefficients of a model that was trained using principal component analysis. Okay, the second component of the tutorial, we're going to use write a function that creates a TF-IDF representation of a corpus. And you're going to use your function to cast the Rotten Tomatoes dataset to a TF-IDF representation and retrain the logistic regression model from the tutorial using this representation. Remember, the advantage of TF-IDF is that you take advantage of the context when you're speaking about what the meaning of a word is, right? So it's a contextual representation of the text. Okay, so let's hop here to the second part of the tutorial. This has to do with model optimization. So remember, in the previous section, what did we see? Well, we saw that the logistic regression, when we were using ElasticNet, for example, was very sensitive to the settings of the hyperparameters. That is to say that the AUC went from being something which kind of stinks, which is 0.68, to 0.8 something when we tuned those hyperparameters effectively. Okay, but here's the thing, right? We've taken it for granted up until this point that the model, given those hyperparameters, is always just going to figure out the optimal values of the parameters totally on its own. So more specifically, we had discussed that as long as the model has some data, this logistic regression, and it knows a loss function, then it's going to be able to kind of find the optimal values of the parameters given that notion of loss. Okay, let's actually spend some time here exploring exactly how the models determine the values of the parameters. And so to begin, let's assume that we have some data. This is the same data set we talked about in the lecture, where we want to relate the number of exclamation mark characters in some text to a binary indicator of whether the text is happy or not. So I've got the data here. I'm going to import it, and I'm just going to plot it so that you can see it down here. So it's a pretty simple data set. Again, there's a binary outcome for whether the text sentiment is positive or negative. And then there is a number of characters shown here along the x-axis. Now, because this is binary data, there's a lot of points that are overlapping, obviously, in the data set. And so I colored the points here. I made basically the opacity darker if there were more points overlapping and lighter if there were less points overlapping. Okay, now at a glance, it's obvious that a sigmoid is a good fit for this, right? I mean, if I kind of move my mouse over this, I need something that's going to saturate after a certain point. It's got to have a slope on it. So sigmoid is a great way to model the relationship between x and y. And a sigmoid, as you recall, is modeled by this equation here. Okay, the y hat refers to the predictions by our model. This is what distinguishes them from the actual value of the data y. And the m and the b parameter here are coefficients or parameters of the model that help us precisely tune and optimize for the relationship between the x variable here and the y variable here. Okay, let's go ahead and actually just write out this equation for a sigmoid as a function. So I can write it out here. And let's plot that function to make sure that we did it right. So I plotted it here, and yeah, that does look like a sigmoid, right? I mean, I chose some random value of m and b here, shown up here in this code block, and I just plotted it, and I can see that, yes, it's a sigmoid, in fact, because it's between a value of 0 and 1, and it's nice and smooth, and so on and so forth. Well, one very naive thing I could do is just kind of plop this sigmoid with the random parameter values that I chose of 1, 1. I could just stick it on top of my data set, and if I did that, here's what the fit looks like. Now, you can tell just with your eyes that this is a bad fit, right? The blue line, you want it to go through as many of these purple points as possible, and when the purple points start showing up at the top and the bottom, that's when the slope of the line needs to start coming up, okay? That's not what's happening now. So clearly we need to tune the values of the parameters here. Okay, well, as we discussed in the lecture, one thing we can do is we can just iterate over many values of the parameters. That's all I'm doing here. I'm saying go over many values of b, and let's just plot the line. And this image here should be familiar from our lecture. You can see I've plotted each of the colors of the lines corresponds to a different value of b when I held m at 1. And this red line sort of stands out as the winner among the set. So one thing I might do is I say I'm just going to keep this value for my b at -7, and now I'm going to go about optimizing for m by, again, just plotting a bunch of lines for m. And what you can see is that m is sort of controlling something about the slope of that line, whereas b was sort of shifting it to the right and to the left. And so it looks like this purple one here is sort of the best fit, which is when m is equal to 0.9. So it seems like we have our winner, right? Maybe the best fit for this, if we just had to use our eyes, is m is equal to 0.9 and b is equal to -7. Okay, and in fact, I can just take the model and I can plot it. You see, plot the sigmoid for exactly those two values, the 0.9 and the -0.7 from the function I created earlier. And look, it does seem, in fact, that it fits pretty well. Okay, but the problem with this is that even though it looks good intuitively, you have no way of knowing if it's actually the best fit possible. Best requires a formal way to measure something, right? For example, if we wanted to figure out who was the tallest person in the class, you need a ruler, right? You can't just say, well, I'm just going to, intuit, and everybody's going to have their own random intuition for what is tall and what is short. You need an agreed definition, inches, meters, something else. And so similarly here, we need an agreed definition for what we're going to use to assess how well this line fits given the data that we observed, okay? This is exactly what a loss function provides us, okay? It's just a way to measure the probability of this data given the model, or if you're working in a Bayesian sense, it's the probability of the model given the data. And now you may recall, as again from the lecture, that the particular form that we use in logistic regression is called cross-entropy. So I've written out cross-entropy here. I want to remind you that, as we did in the lecture, the y's that you see multiplied here and the 1 minus y is basically a mathematical shorthand for writing out an if statement. Because if this y is 1, this term goes away, and if y is 0, this term goes away. So I could write out the cross-entropy loss function actually here directly from this equation as I show you down here in the code block. Okay, now notice that the cross-entropy function computes the loss for a given pair of y and y hat, exactly following the equation up here. So if you wanted to compute the loss for an entire data set with many x's and many y's, what you'd do is you'd say, okay, well, all I'm going to do is I'm going to take my model, I'm going to pass in the values of m and b, and I'm going to compute a bunch of y hats. And then for each of those y hats and the actual y's, I'm going to compute the cross entropy, and maybe I'm just going to sum them up. Okay, that's a totally valid way of saying what's the loss for one model versus the other. Okay, so let's sanity check this by comparing the costs for two settings of the parameters that we were looking at earlier. Remember we said, okay, I'm just going to randomly guess when m is 1 and b is 1. Look what the loss turns out to be. Oh, it's 287. That loss is much higher than when we did our visual optimization of the parameters at m equals 0.9 and b equals -7. So what does this tell you? Well, exactly what we've been saying in the lecture, that when the loss is lower, the fit is better, and we now have a nice ruler that we can use to precisely measure one setting of the parameters against the other that's not as subjective as sort of glancing at it with our eyes. Okay. Well, now that you have a loss function in place, we can more thoroughly explore the relationship between the parameters and the cost function, right? Or the loss function, as it's referred to. Cost and loss function, by the way, are sometimes interchangeable, depending on the community that you're operating in. Okay, and we could just do that with a simple grid search, just like we did with the hyperparameters, correct? So we could say, hey, I'm just going to go over every possible value of m. I'm going to go over every possible value of b, and I'm going to just sort of check to see what the loss is at each of those points, okay? And I'm going to append it into a nice matrix, and then I'm going to plot a heat map for it, okay? And what do you see here is that heat map. So what I've done is the y-axis here is different values of m, and then the x-axis here is different values of b. And each of the little cubes that you see in this two-dimensional grid, I basically computed the loss according to the function that we wrote up earlier. I mean, I computed it myself. There was no package we had to import or anything. We just computed it ourselves together. And what you can see here is that this surface, just by glancing at it, I can identify the optimal location for the B and M pair that minimizes the loss, and hence it fits the best, right? So it'd be somewhere down here, right around here. Okay, specifically the best location according to at least this grid is where B is -8.6 and M is 1.16. That's pretty close actually to our visual inspection, right? Our visual inspection, we said it was going to be 0.9 and B was going to be -7. So these two numbers are pretty similar, right? Okay, and that's good because if they weren't similar, then I would think that my eyesight is even worse than it is. But all joking aside, like the real question here is the results that we find, when we use this optimization approach, is this better than when we use the regular approach, right? So, and we're going to compare that here by just comparing the loss in a moment. But before we do that, in the previous part of the assignment, we kept talking about regularization, right? And how regularization changes the value of these parameters that we find because it adds a penalty if these values get high, right? So I can come here to my cost function. This is the exact same loss function or cost function that I wrote out earlier, and I'm just going to update it to add an L2 regularization. This is the L2 regularization. I literally just took B, I squared it, and then I took M and I squared it, and I added it to the cost that came from the cross-entropy of each of the y hat and y pairs, as you can see up here. That's it, right? That's all the regularization was. Okay, and if I replot that heat map, what do you see? Well, this optimization surface, or this loss surface, I should say, looks very different now. The optimal value of M and B has changed from whatever value they were before. I guess it was minus 8.6 for B and 1.16 for M. It's now B of minus 0.1, which is way smaller, and M of 0.18. Okay, so clearly optimizing with respect to this new loss function that has the L2 regularization term gives us a different set of M and B, which are much smaller. That is, it dragged some of the coefficients that were not as relevant to solving the problem closer to 0. Okay, so I just want to make this clear that this is sort of exactly what the regularization is doing and how it accomplishes what it's doing. Okay, well, in these previous examples so far, we've been using grid search, right? So by grid search, I mean I choose some values of B, and then I choose some values of M, and I just iterate over them with a bunch of for loops, and I compute the loss. Okay, that's all great. This is, well, it's great insofar as you only have a very small number of things you have to optimize. Where it starts becoming not so great is when the number of parameters that you have is bigger than 2. So we just have M and B in this case, but what if we had more features, right? What if we had as many features as we did in the bag of words representation from the earlier part of this tutorial? So let's say we had the 18,330 features that was from the Rotten Tomatoes movie review set. Well, if we even made our grid search incredibly tiny. So we basically said we're only going to, along each of those axes, check 2 possibilities. So we made just, the resolution of the grid was horrible with respect to each of the axes. We would actually, to search that grid, we'd have more possible parameter settings that we'd have to check than there are observable particles in the universe. This is actually the number that you'd need. Again, this is just if you wanted to search 2 values, just 2, along each of the axes in the bag of words representation, right? So I mean, this is an insanely large number of things. You probably could not explore all these possibilities. So what this tells you is that you're obviously going to need a better way to optimize the value of parameters other than a grid search. Okay. Now, you probably recall from the earlier image where I showed you the loss with respect to M and B, that there was this nice smooth convex gradient on the loss surface, okay, with respect to M and B. So that is, the loss grew consistently higher as we moved further away from the optimal M and B. And so if we just had a way of measuring the slope on that surface, we could always follow it down, right, to the optimal location, the place where there's the minimum amount of loss. More specifically, we could just literally start at a random point. We could check the gradient at that point. If the gradient is 0, we could say, hooray, we've hit the bottom. And if it's not, we're going to take a step in the direction of the gradient towards the bottom. And we're just going to keep repeating this until we hit a point where the gradient is 0 or very close to 0. This process is gradient descent. That's all gradient descent is. And it's very, very simple to actually implement yourself, as we're going to see here in a minute together. Okay, so how do you get the gradient of the loss? Well, there's actually 2 ways to do it. I want to verbally tell you here that computationally, one thing you could do is you could, if you want to get the change in the loss with respect to M, you could just put in a value of M and then put in a slightly larger value of M. And now you'd have the change in the loss with respect to M, right? Delta loss divided by delta M, you now have the change in the loss with respect to M, and you're done. And you can computationally do that extremely simply. A lot of the ways that people will show this in machine learning textbooks, which is why I'm going to show it to you here to demystify it, is by actually writing out a formal derivation of the loss, change in the loss with respect to the parameter value, okay? So I'm going to just show you that here, But again, I want to remind you that if you want to analytically or computationally approach the solution, you can just very simply put in a value of your parameter, adjust that value by a tiny amount, check what the effect is on the loss, and you now have the change in the loss with respect to the parameter. Okay, so now having said that, let's go through the formal derivation of it. So let's say I want to compute the partial derivative of the loss with respect to one of the parameters in our model. Let's say it's m, because it was mx plus b in the sigmoid, if you recall. Okay, well, when I take the partial derivative, I can obviously break it up into these two components. When I'm doing the partial derivative, it's the partial derivative of this side and the partial derivative of this side with respect to m. Okay. Now what I'm going to do is, to begin, I'm going to substitute the y hat here with the way we're estimating y hat. That's a sigmoid, right? And the equation for a sigmoid, I've written it here. So we've got the m, and we've got the b, and we've got the x, and we're all good to go. Well, now that we have it like this, we can actually take the derivative with respect to m, which shows up in this equation, and we get this consequence down here. Okay. Now, you can move around or restructure the way that these sigmoid or sigmoid-like components of the equation are written, okay, so that you can redefine things in terms of y hat again. So all I've done is I've done a small transformation of this thing to turn it into this, okay, and a small transformation of this object to turn it into this. They're equivalent, actually. If you go to Wolfram Alpha or you put it in your graphing calculator, you're going to see that these two are the same, okay? And this is now y hat again, so I can just rewrite it for short as y hat. And finally, I can simplify this to get the final definition of what the change in the loss is with respect to m. Okay, and just as I did it with m, I could similarly do it with b. Now, what's the advantage of having this closed form for the change in the loss with respect to m? Well, I could set this equal to 0, for example, and then, solve, for example, for an optimal value if I wanted to. Now, having said that, of course, you can also just use this equation here, right, directly to compute the gradient for any value of y, x, and y hat from our data. So I could come here and I could just write out a function that this is literally me writing out this equation that you see here just as code, okay? And this other equation for b, I've written it here just as code. And I've rewritten out, actually, these are not new, but these are just me rewriting the cross-entropy cost function, the total loss, computation of the total loss, and the sigmoid, just so that you kind of have all these together, because these are the necessary components for doing the optimization of a logistic regression from scratch. Okay, and now we can go about performing gradient descent optimization of the parameter values instead of doing the grid search, right? So what I'm going to do is I'm going to initialize some data. Okay, I'm going to set some initial values of the parameters. I'm going to choose a learning rate that just says how much am I going to step. You may recall from the lectures how much do I step when I want to update the parameter values. So for example, if this learning rate is 0.005, let's say the gradient in the direction of m tells me that I need to step in the positive direction. This would go to 1.005. Okay, that's what the learning rate does. It updates your parameter this much. Okay, and so then I have a certain number of epochs. This just basically says how many times do I want to do these steps of this size for my parameters. Okay, I'm going to save the values of b and m so I can plot them later, but then here's the optimization approach for gradient descent. I'm going to first compute the values of y hat. Okay, so given the value of m, given the value of b, given all my x's in my data set, I can compute a set of values y hat. I can then compute the gradient. Okay, so that's what we had. Remember, just up here, I'm computing these gradients. Okay, and then I'm going to take a step in the direction of the gradient. So if the gradient is positive, then I'm going to step negative, and if the gradient is negative, I'm going to step in the positive direction because I want to go down. And I'm going to do that for both the m and the b parameter. Okay, and then I'm going to append the results of the m and the b that I find, and I'm just going to keep iterating over this so I can take many steps. Okay, so if I actually plot out the values of the parameters when I perform this approach, look at what I get. So that in this case, the orange line is M and the blue line is B. You can see that for a certain number of iterations, or epochs, as I called it in the above code, the parameter values end up converging after a certain number of epochs to a stationary value. In this case, the best value for B was -12, and the best value for M was 1.7. Now, you may recall these are pretty close, actually, to what we arrived at for the grid search. Okay, for the grid search, I think it was 1.16, and the B value was -8.6. Okay, it's not identical, but it's close. So, but because we did this with gradient descent, it stands, and gradient descent, we made those step sizes much smaller than the size of the grids that we were evaluating. You'd think that we'd be able to optimize more effectively using this gradient descent approach. And we can actually test that by just computing the loss of the parameters that we got with gradient descent. In this case, it's 13, versus the loss that we got when we used grid search, which, as you can see, is closer to 15. So what this tells us is two things. It says that the gradient descent is not only more computationally scalable with the number of features, because we don't have to explore all these random places that may not be relevant to us, but they even provide a better answer. Okay, so for learning exercise 2, what I'm going to ask you to do is explore some of the parameters in the code that we wrote together above. Specifically, I'm going to ask you to, using the exact same simple data set and the implementation of the logistic regression from this tutorial, just change some of the learning rate and iterations or epochs, and comment on how the convergence of the algorithm changes as a function of those settings that you explore. Okay, it's up to you. You can choose 2 or 3 to demonstrate. I've intentionally left this open-ended so that you can explore. Okay, the second thing that you're going to do is you're going to come up with a generalization of the logistic regression model that I showed in the previous sections of this tutorial. Because the issue with my implementation was what? I only have M and I have B. And I did that because I wanted to help you really understand how does a logistic regression work? How is a logistic regression optimized? And we didn't want to get bogged down in linear algebra notation and other things in case you don't feel as comfortable with that. But what I'd like you to do now is come up with a way of generalizing what we wrote in this section of the tutorial. So instead of assuming that we're only going to pass in one feature X, and we want to find the relationship between that and Y, assume we're going to pass in a data set X that has n columns and a binary target vector Y. And you need to write some code that's going to determine the value of the n+1 coefficients using gradient descent. Okay? The last thing that I want you to do is, when you write your general purpose logistic regression up here, I want you to compare your implementation to bag of words. I want you to compare your implementation against sklearn, the one that we did earlier in this tutorial, when you're classifying the Rotten Tomatoes movie review data set. And to keep it tractable and to prevent the size of your data from exploding so you don't have the 18,000 dimensional object, I want you to just transform the bag of words representation using PCA and keep only the first 10 principal components. So you should have as many rows as there are sentences in that data set and just 10 columns. That's it. Okay? Okay. Now, the third part of this tutorial is going to deal with neural networks. Now, in the previous section, we wrote a sigmoid function. We took a given value of X, B, and M to generate a single evaluation of the sigmoid function. But our previous implementation was not flexible or generalizable, right? I mean, we already discussed that, and that is what you're going to be doing for the purposes of the learning exercise. So a first step in, by the way, solving that problem for the learning exercise is to just generalize the sigmoid function, right? So the sigmoid function, what it actually wants to do is take in a set of parameters, beta, and then have a set of data that it's going to multiply basically the each of the column values in the data set X with a parameter value in beta, and then add an offset term, beta 0. Okay, and then it's going to run that through the sigmoid, just as we did before with the mx plus b. Okay. Now, these simple sigmoids have decent performance when we can assume there's a monotonic relationship between the input and the output. But as we discussed in the lecture, there's many instances where that's not true. Okay. So we talked about, for example, tweet classification in the case of the lecture. But another example is, let's say I wanted to predict your mood, good or bad, given the number of pizza slices you consumed for lunch. Well, for a 1 unit increase in pizza, the probability of your mood being good is going to increase, but only up until you become very full. And then after that, every 1 unit increase in pizza consumption is going to decrease the probability of your mood being good. And a simple logistic regression is not going to be able to capture that kind of relationship. Okay, so one approach we could take to solve that problem is to say we need to write out a brand new model. And anytime you're building a model, you want to think about the properties that you want that model to have, and then see if you can use existing components that you're familiar with to kind of build a line or an object that can flexibly accommodate that. So in our case, we're going to need some areas that increase, some areas that decrease, and other areas that are flat. And so, well, we might want to use a weighted average of sigmoids, for example, as you recall from the lecture. Okay, and W here just refers to the weights we're going to use when we're combining the sigmoids. Okay. Now, the problem is that if we want Y to remain a classification or a probability, like a class or a probability, we don't want the value to go above 1. And so we can just wrap it in another sigmoid here to keep it stable. Okay. And if we just, for some random values of W and some random values of the sigmoid values, which are the betas, if we just kind of plot a bunch of curves for some random values, look what you see. You can see that that model can accommodate a variety of forms, right? And one of those forms is actually, looks like it's a pretty good starting point for what it is we want to accomplish, the orange line here, right? So again, each of these lines here, I just took the equation above, I wrote it out by hand myself, okay? So you can see here I've got, a sigmoid of a sigmoid. So I kind of take some coefficients, I take the sigmoid of the data and those coefficients, I concatenate them into another data set, and then I apply another sigmoid on top of it with some new parameters, and exactly as I described in this equation. This is an exact implementation of that. And then I just randomly chose some parameters and plotted it, and you can see that I get something that could probably be used, right, if we just tune those parameters a little better with, for example, gradient descent. Okay. So in the previous section, we observed that, 2 layers of sigmoids, that's what created these lines. It was 2 layers of sigmoids. It was pretty flexible, right? It gave us more flexibility than a single sigmoid did. And so it stands to reason then that a sigmoid of sigmoids would be even more flexible. And so we don't have to, limit ourselves to just using, 2 layers of sigmoids or 3. We can use as many layers as we need so that we can get this line to sort of be as crazy looking as we need it to be to fit any kind of data. That process of stacking these simple functions together to create more and more complex functions, that's the entire intuition behind neural networks. That's everything you need to know if you want to understand how they're built and why they're built the way they are and why they're as flexible as they are. Okay, now if you're going to be using these models practically though, you could write, by the way, a lot of the really cool tools that exist in science, they're written actually very similar to what I've done here. And then they just write their own version of gradient descent. And I wanted to put you through this so that if you go read a paper and somebody writes it out like I did here, you won't be flabbergasted by it. But if you want to train these for a lot of practical purposes, there are some tools that can make your life easier, such as Keras and PyTorch. I'm going to, for the purposes of this tutorial, talk about PyTorch just because most people tell me that PyTorch is easier to learn if you've never sort of dealt with these neural network packages before. Okay, so you can import Torch using a line just like this. And then you can use Torch to compute, for example, the gradients in some output with respect to the input. So for example, what I'm going to do here is I'm going to just make it extremely simple. I'm going to say I have M1 and B1. These are two parameters in a model that I care about. And then I've got some random data X, which is just, this is just some data that I created for this demonstration purpose. Then for each of those values in X, what I'm going to do is I'm going to convert it to a tensor torch, a torch tensor. And then I'm going to compute the value of Y using X and the parameters, right? So I compute the value of Y using that. And then I can get the gradients using something called back propagation. Okay, that's basically how you go about performing the collection of the gradients using the chain rule. I'm not going to cover it here in the lecture, but you're welcome to look into that a little bit more on your own if you're curious how back propagation works. There's excellent explanations that are available online and in many books. Okay, but anyway, the whole point of this back propagation is to get the gradients, right? And once I have the gradients, I can store those gradients and I can do things like plot them. So what I've done here is I've just shown you that I can, for example, for the sigmoid, go about computing, for example, the derivative of that sigmoid, which is obviously going to be very high here where it's steep. And as it sort of flattens off, it's going to get closer and closer to zero, right? So this is just to show you that tools like Torch provide pretty straightforward ways for you to go about computing things like the gradients in case you're interested in that sort of thing. Okay, well, in addition to just providing a way to compute the gradients, Torch actually has some built-in neural network modules that you can use to sort of build out networks and explore them. I think in order for us to understand how Torch works, we should just start with a logistic regression because that's what we've been covering in the tutorials up to this point. So I'm going to import a bunch of Torch libraries that we're going to need, and I'm going to define a logistic regression model in Torch notation. So what you do is you write this class definition. This class here, this is not something from Torch. I could change this name to, XYZAAA, right? And it could still be a logistic regression. This is something you define, okay? I've written it as logistic regression, of course. And notice that what it does is this imports from this neural network.module, which is a Torch class, okay, in this part of their library that basically facilitates all of the neural network operations. So the first thing that you do in this is when you have a class, this init thing is called anytime you initiate the class. So when you first kind of call it in your code, everything here is going to get run. It's going to say, first go ahead and, grab everything from the neural network module, initialize everything in the neural network module. And then what I want you to do is I want you to keep track of some weights. Okay, now remember, the weights in the case of a very simple logistic regression are just the M and the B, right? It's the stuff that's in the bottom of the sigmoid inside of the exponential, okay? And so those weights are actually linear. I mean, the equation is not linear, but the weights are linear, or the parameters are linear. And so I can store those linear weights or linear components in this object self.linear. Okay, now this says, kind of tell me what you want the layer to look like, okay, or the parameter to look like. And then this says, tell me how I combine those layers or parameters together so that I can compute the output. And so obviously what we need is, when we want to compute that, is we want to take a sigmoid of that linear function, right? That's exactly what we did when we wrote this from scratch ourselves. We took a sigmoid of a very simple linear function, mx plus b. Okay. Now, okay, this is our logistic regression model, and we're going to see in a moment, sort of how we formally train this. But I should note here that this object, for example, neural network.module, has ways to do assessments when you define a model like this, but it does not have a formal way that you go about doing the training or evaluation. You have to write those from scratch yourself. So I've done that here. Now, I want to point out that this way of writing out the training function, this is literally identical to what we did when we wrote this from scratch ourselves, okay? It's just that the notation here has changed so that we're using some things from Torch, okay? This is actually one of the reasons why I wanted us to go through the exercise of understanding how to write a sigmoid from scratch and stack the sigmoids and do the gradient descent, was because I didn't want this Torch notion and Torch notation to confuse you. Okay, so anyway, I've done here is I've written a function called train model. And this takes obviously a model. This is the logistic regression model in our case. It takes some x's and y's, then it takes some hyperparameters. Okay, and what the model does is it says, tell me the loss function from the hyperparameters. This could be gradient descent, right? So there's some standard kind of built-in gradient descent. I'm sorry, this loss function is cross-entropy. The optimizer is gradient descent. Sorry about that. Yeah, so the loss function here could be cross-entropy, and then the optimization function here is, for example, stochastic gradient descent, which is just a form of gradient descent. Okay, we tell the model object in Torch that we're going to start the training, and then we're going to iterate over our data as many times as there are epochs, just like we did in part 2 of the tutorial. So for each of the epochs, we're going to clear out or zero out the gradients. We're going to compute y hat from the model of x, just like we did in the previous part. We're then going to compute the loss, and we're then going to compute the gradients, and we're going to take a step in the direction of the gradients. And for plotting purposes, I'm going to save them. And that's all this training function is going to do. And the evaluation function is going to take our model, x, y, and some hyperparameters, and effectively it's going to compute the accuracy. That's it. Okay. Okay, so let's try this out. The first step that we'll need to do is convert our data into PyTorch's tensor format. Okay, I must say, in my opinion, just figuring out how you convert the data into their format is one of the trickier things that I remember I struggled with when I first started working with these libraries. So I've included an example here. I took the exact same dummy data set that we used earlier in the tutorial, and I've shown you how I'm going to cast x and y into the correct tensor objects that are needed to go about training the logistic regression. Okay, now remember, we have hyperparameters for neural networks, just like we had hyperparameters when we were doing regularized logistic regression. Some of those hyperparameters are, for example, the random seed. This is going to say, where do we start the initialization of the weights? The m and the b in the case of the earlier example. Do we start it at 1, 1 and then do gradient descent? Do we start it at 12, 12? Where do we start it? And this random seed will help determine that. There's a loss function. In this case, BCE stands for binary cross-entropy loss. This is the same one we discussed in the course. And then there's a learning rate, which we've also discussed, and the number of epochs we want to take. So I've just stored these all in a dictionary, and I pass it to the training function up here so that it can kind of take advantage of those hyperparameters, and we can decouple some exploration of these hyperparameters from the formal training process by just changing the values in this dictionary. Okay, that's all. So now, once you have all this set up, training the logistic regression model using Torch is actually very simple. You say, okay, I'm going to set the seed using the random seed value that I specified in the hyperparameters. And now I'm going to create the model using, in this case, the input dimension is 1 and 1 because I'm mapping from x to y. Okay, so I'm going to then train the model using the function I did. It's going to return the model and the losses, and I'm going to compute the accuracy by evaluating it on x and y. And what you can see is that if I plot the performance of the model, hey, it does pretty well, right? I mean, you can see that the loss of the function decreases with the number of epochs of training. So what that means is that the value of the parameters we identified gets better and better as we let this thing train more. Okay, now recall that in the previous section, when we were dealing with this same dummy data set, the optimal value of the parameters we arrived at were -12 and 1.7. If we just plot or print the value of the parameters here, you can see that they're very close to that. So this is just a basic sanity check so that you feel convinced that what the torch logistic regression model is doing is literally providing the exact same thing that we came up with on our own. There's no differences between what they're doing and what we did together, okay? It's just that they're a package that helps you do it. Okay, so now let's finally move to neural networks. Well, remember we had talked about an example data set in the lecture where we said, we may have, for example, the characterization or the classification of tweets given some data X, and we want to predict the class of that data Y. Okay, this is a great problem for a neural network because a simple logistic regression just won't be able to fit this. Okay, well, I'm going to go ahead and first cast this training data for this new problem into Torch. I'm doing that again here. And then I'm going to define a very shallow feed-forward neural network that consists of 4 layers. It's 1 input, 2 middle layers, again known as hidden layers, and then an output layer. So here's those layers. Here's the input to the hidden layer. I've specified it here. It has some weights, right? It's a linear function. Then the second fully connected layer also is going to have some weights that are linear. The third is going to have some linear weights, and the fourth is going to have some linear weights. And the way that I'm going to combine all these weights that get specified up here is as follows. I'm first going to take the input and I'm going to pass it through whatever the weights are that define the linear functions from this first one, and then I'm going to run it through a sigmoid. And then I'm going to come to this middle layer here. I'm going to pass it through the weights that describe that middle layer, and then I'm going to pass that through a sigmoid. And then I'm going to pass it through the second middle layer, and then pass that through a sigmoid, and then pass it through the final layer of linear activations, again through the sigmoid. So you can see the way that you make the net deeper and deeper in Torch, this is sort of why people think it's easier, is you just keep stacking these to make it deeper and deeper, instead of having to write out, for example, a cumbersome equation. So if you can get used to the syntax here, it'll make training networks of different levels of depth pretty straightforward. Now, just as we did before, let's train the models using the model train and eval model functions we wrote earlier. I've set some parameters of the model here. This is for the logistic regression, and this is for the new neural network that we did. And I'm going to compare their performance, okay? Well, what do we notice? If I, again, plot the loss as a function of the number of epochs of training, you can see that while at first, for the first several epochs of training, the logistic regression and the neural net do about the same, eventually, given enough time, not surprisingly, the neural network beats the logistic regression and is able to find a way to optimize the settings of the parameters that give it better performance. Okay. Now, I want to make something very clear. These long periods where the model performs the same with respect to a simple baseline like a logistic regression, there's a whole host of reasons why this could happen. Okay, but oftentimes one of the suspects is your learning rate is bad or your initialization of your weights is bad, because there's nothing magical about neural networks. Okay, they're universal approximators, and they're using some version of stochastic gradient descent or regular gradient descent to try to optimize the value of the parameters given the data. But because there's surfaces, the loss surface is kind of complex or not smooth, it may not find those quickly depending on how you initialize the weights. So let me give you an actual example. All I'm going to do is I'm going to rerun the example we saw above, but I'm going to change the random seed. That's literally all I've changed in this code block here. Everything else is identical. What you notice here now is that if I compare the loss of the two over time, look at how many more epochs of training it takes before the two models start to finally diverge in terms of their performance. Again, the reason I bring this up is because if your model, your neural network model that you train for any purpose, either in this class or outside it, is not able to beat a very simple baseline model, it's probably because of something to do with an unlucky setting of the initial weights, or something to do with your learning rate. Okay, now having said that, what you're going to do for the third exercise in the homework assignment is to specify a neural classification model. Specifically, you're going to take a neural network that maps a sparse bag of words representation of the Rotten Tomatoes movie review dataset from part 1 of the tutorial into the probability of the movie being positive or negative. Okay, the second part of this is you're going to train and evaluate the model. So to be very clear here, you're just going to write out the actual definition of the model in torch notation. I've included, by the way, an online example for doing this with bag of words. This is for a logistic regression, not for a deep net. So I just want to warn you about that. You need to do it with a network, okay? And I'm going to leave it up to you, by the way, how many layers and how many nodes you want to use in that network to optimize the performance. Okay, then you're going to train and evaluate the model, and then you are done. As you go through your homework, don't forget that at the end, you should fill out each of the self-assessments. And once again, please be honest as you fill those out.